So hi, my name's Iaizzi. I guess I can't say thanks for coming, but thanks for watching. And today I'm here to talk to you about quenching to field-stabilized magnetization plateaus in the unfrustrated Ising antiferromagnet. Now, normally the chair would have to say that, and when I had to say it out loud, I realized a better title would be "Stable Frozen States Without Disorder." And I want to say at the top, so I don't forget, that I want to encourage any of you, since you can't ask questions, since this is a recording, that if you do have questions for me, I'd absolutely encourage you to contact me. There's my email address, which should be on both slides, and it's my website on the final slide. And then I also normally wouldn't put a picture of myself in my own talk, but then something feels strange about giving the talk and not having people be able to see who you are. And so, anyways, there's a picture of me. I still feel strange about it, but let's get into this. So I'm going to talk to you about the 2D Ising antiferromagnet. And so you start with the square-lattice Ising model. And in this case, we're focused on the antiferromagnet. So the ground state's this twofold degenerate, either up, down, up, down, up, down, or down, up, down, up, down, up. There's the phase transition. This is the simplest model with the phase transition. And then what we're going to do is add a field. And so it turns out that very few people have studied this case. And the reasons aren't entirely clear to me, but I think one of the reasons is that for the case of the ferromagnet, the zero field, the ferromagnet and antiferromagnet have an exact one-to-one mapping between them. And so if you understand the ferromagnet, you know everything about the zero field antiferromagnet. But then actually, when you add the field, it breaks this transformation. So that, somehow no one's really looked at this. And I like to say that this has been a theme of my research, is taking something that has not had a field added to it before and adding a field to it. And very often, no one's done that before, and very often something interesting happens. And it's great if you're not particularly talented or hardworking, like I am not, then you can use this as your sort of entire research career. Although perhaps I shouldn't be telling people that. But anyway, so the sort of mean field or like equilibrium behavior of the system is very easy to understand. So at zero field, you have this, and zero temperature, you have this ordered state. And then as you add the field, nothing happens until you reach the saturation field, and then half of the spins flip, and then all the spins are fully aligned. Now, obviously, I'm not about to give you another 10 minutes of talk where that happens, because that would be very exciting. So pretty crucial to what we're doing here today is the dynamics. So we use Metropolis Monte Carlo with the single spin flip updates. So you choose a spin at random, you flip it with this probability. This is the Metropolis choice. If you've ever written a Monte Carlo program, this is probably the one you wrote. And it's very easy to write this code, and it's kind of fun to play around with. And then we're going to do a quench, which is you start from an infinite temperature state, which is just a totally random arrangement of spins, and then you do an instant quench to some temperature T, and then you do the Monte Carlo updates at that temperature. And although I say quench, really what I'm doing is the simplest thing you would do if you just set the temperature to something and start your Monte Carlo simulation. That's what will happen. And so what happens? So here's again the prediction we have from the theory. And it turns out that's not what happens. So here in this figure, we have magnetization as a function of field. Every point, for a few different temperatures, and every point along these lines is hundreds of simulations, independent quenches, and averaging over the results of hundreds of independent quenches. So, and at high temperatures, so this beta equals 2, that's relative to zero temperature, pretty high. You kind of get what you expect, which is that this this dark blue line, or medium blue line, the jump that would happen normally at h equals 4 is smoothed out by the finite temperature, and that's it. But as you go to lower temperatures, something strange starts to happen, and so you get these plateaus. And then at the lowest temperature, beta equals 64, now you have these very flat plateaus, and then in between at h equals 2 and just below saturation at h equals 4, you get the correct ground state back. But in the middle, you have these very stable, long-lived plateaus. And so this is like a total breakdown of ergodicity. And actually within these plateaus, the simulation arrives at a state and then it's stuck there forever. So there's no dynamics at all, basically. Everything freezes. And here I want to point out that I've added no intrinsic disorder. There's no disorder in the field or in the parameter, in the couplings. The only disorder is the random spin state you start with. And so what is actually happening here? This is very strange. And so, one more point I wanted to make here, which is that, so because each point along these lines, so here, for PowerPoint, or for this slides, I made it into a continuous line because it's easier to see on a projector. But for each point along these curves, it's totally independent simulations, and the error bars here are extremely small, smaller than the width of the line. So okay, so we can extrapolate the zero temperature magnetization from this chart. So basically, you have a plateau from 0 to h equals 0 to h equals 2, and then you have another plateau from h equals 2 to h equals 4, and then you have these points at h equals 0 and 2 where you get the correct ground state back. And then the saturation point is kind of interesting, although I don't think I'll have time to talk about it today. And then from here on, I'm just going to talk about zero temperature. So what's interesting I want to point out is it's ergodic for h equals 0, plus or minus 2, and plus or minus 4. So what is actually happening? So here I have two movies for you. The first one on the left is basically a simulation starting from a totally random state and arriving at a state in the first plateau, which here h is set to 1. And so there are pluses and minuses to show you the spin state, and then the coloring in the background will show you which of the two antiferromagnetic ground states each spot is in. So you see, you start from a totally random state, and we get here, and then we're stuck there forever. I want to be clear that time on this slide, or this movie, is not represented realistically. This is just a selection of states along the way. But this is more or less the path that occurs. And so you can see you can imagine there's some kind of rules here for this final state. So that these domain walls are totally stable. Every single spin here, if you flip that spin, it will increase the energy, which will be important later. And here we're doing the same thing for this h equals 3 plateau. So the final result looks different, but in the end, the way you get there is pretty similar. And we'll come back to these animations later. If you want to look at them online, because the slides that I'm going to post will not have the animations in them, there's that link down there. So what's actually happening here? So for these single spin flip updates, there's only 5 spins that matter, because there's the spin at the middle, which x, that's the one you're trying to flip, and then there's its 4 neighbors, because that decides how much energy it costs to flip that spin in the middle. And so you can sort of just write out all of these states. And so here we've done that. This is going to be very hard to explain without using a pointer, but I've not been able to figure out how to do a pointer with this recording mechanism. So basically each row of this figure here is a pair where the neighbors are fixed because we can't change those, and you basically just look at which state has a lower energy, the one with the middle spin up or the one with middle spin down. And then at zero temperature, you will basically always choose the state where the middle spin has a lower energy. So at zero temperature, you accept an attempted spin flip if it decreases the energy or leaves it the same, and you reject it if it increases the energy. And if the energy doesn't change, this is what I'll call a reversible update, which means that you can flip it, and then later, if you come back to that same spot and the neighbors are still the same, you can flip it back because it doesn't cost you any energy. Whereas if it decreases the energy, once you flip that, you're stuck. You can't go back because that would involve increasing the energy. And what's notable is you have these reversible updates when the field is equal to one of these values that the sums of the nearest neighbors can be. So 0, ±2, and ±4, and that corresponds exactly to these values of ergodicity. And so I want to just talk somewhat briefly about sort of how you can, this picture you can draw here of what is happening. So it turns out at h equals 0, like I mentioned before, you can map onto the ferromagnet. And there's already been there's several papers. I picked these two to cite because I think they do like, the 2001 paper is the one where they first describe this, and the 2009 papers where they have this very nice connection to percolation theory. But basically, for h equals 0, bulk domains and straight line domain walls are stable. And so most of the time, if you do a quench at to 0 temperature at 0 field, you end up in one of the ground states. But 0.3390, so on, of the time, you end up in one of these stable striped states. So this is with periodic boundary conditions. And here, in this figure, you can see that once all the domain walls that are there are straight lines, then there are no more spins to flip, because you can't. Every single spin will increase the energy, and then you're just stuck in that state forever. And otherwise, you reach the ground state. And what's really neat about this paper, this Barros paper in particular, is that there's this connection to critical percolation theory. You can actually predict what the probability of getting stuck in one of these striped states is. So here, in our case, in many ways, it's very similar, but the rules are more complicated and therefore potentially a bit richer. So now, in the first plateau, it's the same rules as before, so straight line domain walls and bulk domains are stable, but also corners, if they have an extra plus spin on the inside, those are also stable. And what this means is you now have a huge number of possible frozen states. Rather than just whatever number of stripes you could imagine generating before, you have this, what I suspect was at least exponentially number of possible frozen states. And notably, only only two states are the correct ground states. The correct ground states are also these frozen states, but the odds of reaching them basically goes to 0 because there are only 2 of exponentially many states. And then the corners host the excess plus spin, so that's where you get this net magnetization. You can tell a very similar story for the second plateau. Basically now the straight line domain walls are no longer stable, but the corners and the diagonal domain walls are stable. And so you have like a set of rules, and you could imagine coming up with a way to generate all the possible states that follow these rules. And again, there's at least an exponential number of them, so that it's very unlikely, starting from a random spin state and doing random updates, that you will end up in the ground state. And by very unlikely, I mean essentially impossible. And even for moderate systems, I found that if you do these quenches hundreds of times, none end up in the correct ground state. And so that's kind of interesting that you can get this really, strong, sort of manifold of disorder. And then at h equals to hs, so this is at saturation point. It's kind of interesting. It doesn't freeze. Instead, the temperature dependence goes away, and you get this phase that's a coexistence of 2 antiferromagnetic ground states and the fully polarized states. I'm not going to talk about this too much more right now, but this is equivalent to what's called the hard squares problem. If you're interested, I can give you a lot of references on it, but this is a problem that's already solved and pretty well understood, but it's kind of neat to have this connection. And so, in conclusion, so we have these instantaneous quenches in the Ising antiferromagnet with the field. We get these stable plateaus without having to introduce any disorder. Within each plateau, all of the spins are unflippable, which means that each spin, if you try to flip it, will increase the energy. And you can describe these plateau states in terms of these stable local configurations. Ergodicity gets restored when the updates that do not change the energy are available. And this is useful understanding when Monte Carlo fails. So this is not a secret that you want to have updates that don't change the energy. That's the idea behind a lot of cluster update methods, is that you are trying to identify groups of spins you can flip without changing the energy, or without changing the energy very much. But it's kind of neat here that we have a very clear example of that that's very easy to understand. And then finally, I wanted to make a quick remark that so Monte Carlo dynamics are not the same as physical dynamics. So we choose the dynamics. Like I didn't invent these rules, obviously, but I set up the rules at the beginning, and I said like, oh, I'm going to try to flip one spin at a time, and I'm going to use this update probability. And there are a lot of different dynamics I could have chosen. And some would not have had this problem. Some would have had a different version of this problem. And the plateau states under these dynamics are local energy minima, which means that any of the updates to the nearby states, nearby here meaning states that are only one spin flip away, will increase the energy. But when I made the dynamics, I chose what states were nearby, and I could have chosen different states. And like I said, I wanted to point out that this sort of has a broader lesson of when you're choosing dynamics, you are deciding you're not deciding the energy landscape, but you're deciding the shape of the energy landscape. Like in this case, I've basically chosen almost deliberately bad dynamics in that I've made an energy landscape where there's lots of little local minima. But you could imagine choosing a different set of dynamics where that would not work out, where it wouldn't happen, which obviously if you want the correct ground state of the Ising model, that's what you would want to do. But I think it's interesting to understand sort of how the dynamics affect what sorts of behavior you get out. And so there's some interesting open questions that you could go to from here. So the first thing, it would be interesting to try to enumerate these plateau states. And in particular, then, you might be able to derive the magnetization in the plateaus, which would be cool, sort of from first principles. And then I mentioned there's that connection to percolation theory in the ferromagnet. It may be that you can make a very similar connection here, and because these plateaus are more complicated, there might be something very interesting there. I've not talked at all about finite temperature scaling because this is a 15-minute talk. I've also not looked at it yet, and I think there's probably some very interesting behavior happening around these, what I've been calling valleys of ergodicity. And then naturally you could try this with other lattices, with other dynamics. In general, you should find something very similar, but there might be, again, richer, more interesting behaviors if you look for that. And so now I wanted to thank you for taking the time to watch this, since you're taking time out of your normal day rather than at the March meeting. And I want to encourage you, if you have questions or if you're interested in this in any way, or if you hated it, contact me, because I want to hear about this. So I currently have a preprint that is on archive and is under review. So probably by the time you're watching this, I've sent in my revised version. But I'm very interested in hearing sort of what is interesting about this. I'm not personally someone who does a lot of classical statmech stuff, and so my goal in coming to the March meeting this year was to get feedback from people who do classical statmech full-time. So I'm normally a quantum Monte Carlo person. So you can find me on the web. You can email me. This QR code will take you to my preprint. And with that, I will say thanks very much for listening, and I look forward to hearing from some of you. Sorry I couldn't meet you in person at the March meeting, but I guess everyone stay safe, and happy physicsing.